This tutorial is a continuation of tutorial 7, where a pendulum was swinging pivoted about a fixed point and hitting a vertical plane and destroying it in meaning incurring damage to the plate. The only difference with this tutorial and the other one is that there I meshed the sphere with shell elements but declared it as a rigid body. Here, because the sphere is very a special type of a object, basically something obtained by a surface of revolution, it can be done modeled as an analytical rigid surface. So keep in mind that analytical rigid surfaces are either have to be as surfaces of revolution, such as what we have here, or extrusion surfaces, surfaces created by extrusion. Uh, okay, so perhaps the first 15 minutes of the tutorial of this tutorial is the same as the one in 7, uh, except that when it comes to meshing, I will only mesh the plate and I will create an analytical rigid surface. Okay, so let's go, but I'll do everything from the beginning. So let's quickly go through this. I already mentioned that. The dimensions are given here. The dimensions and material properties of the plate are given here. The here's the plasticity data, and this is the failure information that I'm using. And the sphere is modeled as an analytical surface. Here's the radius, and the mass of it is 1.75 kilogram, which has to be placed at the reference point, which is that pivot point on the top. This velocity, angular velocity, is not the initial velocity, by the way. That angular velocity is maintained even when this sphere hits the plate and goes through it. Okay, so that's maintained, not initial velocity. And I'm using 5-point integration, the default 5-point integration through the thickness, in spite of the fact that a YouTuber suggested to go to 7 to um, uh, handle the hourglass issues, but I didn't see any issues, so I left it as default. Okay, so keep in mind that in 7 I mentioned that in order to replicate the damage, when it comes to damage criteria, you have to actually ask for both of these lines. Both of these lines have to be requested. If you don't request the last one, the ball will actually not go through uh, the uh, the plate, and it just carries the plate with it. In other words, the failed element do not actually show. The last maybe 1 minute of tutorial 7 actually displays that, tells you what it means. So both of these have to be checked, except that I don't use any particular values. I just leave it as default values wherever these things are. And the validity of these damage criteria that we're using, whether it applies to a problem, that's the user's responsibility. And also the data, of course, is inputted through experimentation. And here's the limitation of the analytical surface, as I pointed out. So let's go ahead and create our model. I'm going to start with a assembly with the 2 parts here, and I'm going to right click, insert a 3D part, and that's going to be my plate. I'm not going to rename it, but it's going to be the plate. Basically, this is going to be the plate. Well, maybe I should rename it. I'll call it all right, plate October 15, 2023. Okay, so this is the reference. Copy instance. I'd use same name. It's just that it makes things easier to find when you need it. All right, let's go and make it. Double click on that 3D shape. On that vertical plane, I will sketch a square, and the dimension of a 200 by 200 millimeter by 200 millimeter. Exit. and put a surface on this. Because I'm already in generative shape design, I can immediately put the surface here. But if I was in part design, they would have to switch to generative shape design or something that does surfaces basically and continue with that. So here I'm already there. So under the under the extrude, oh no, under the fill, because I want to fill this thing with the surface, and then say OK. There we are. While we are at it, let's apply the material properties. So let me go to the tools, and where is my material properties? If you can't see it, go to the right. There's an arrow here. It takes you to the other stuff that you can see right there. Create a material, and I'm going to call this thing plate. Exactly the same name. You don't have to. You can give it a different name if you want. October 15, 2023. You say OK. And this is going to show up in the list of your library stuff. So it's right there, October plate, October 15, 2023. I'm going to apply to that part and then check mark and close that. And now we can go and input our material properties. So I go there. Okay. So under structure, under general option, density, 2.77 e to the, well, notice that the unit that's given here was in tons. So in kilogram, it will be 2,770. So because I didn't change my unit, might as well do this thing as 2,770 kilogram per meter cube, which is pretty much typical of aluminum. And then you go to ABAQUS Multiphysics, Mechanical, Elasticity, click on the elastic. This is 70,000 megapascal. 7000, 70,000 megapascal, Poisson ratio is 0.34. Okay, and then you go to damage, ductile metal, and the one that we want is shear damage. Oh, I forgot plasticity. Let me go back. Well, I can go back and do plasticity. Plasticity is up here. Obviously, you can't. Let me actually get rid of this. Let's go to plasticity. I forgot to do that. Metal plasticity, plastic. Yeah, and put those numbers. 120 at plastic strain of 0, which means it's yielding, and this is 240 at plastic strain of 0.3. I could have done this thing later on. And then I go to damage, which was here, damage, shear damage, and let me see now. Here, this was 0.3, and this is 0. What I'm doing is that stuff down here, right there. And shear evolution must be checked, but I'm not going to use any values for it. It's going to be default values. So you click on it, notice that it is requested, it is checked with these default values. And then we say OK. All right, let's do a quick save here. All right, so now we're going to go to the meshing. I don't have to, insert the sphere. I have to do the sphere right there. So we go all the way to the top, right click, insert 3D part. This is going to be my sphere, which will be modeled with analytical rigid surface. Let me call this thing sphere October 15, 2023. Copy, copy. This is the instance, also call the actual part name, same thing, right there. You say OK, and let's go make it. And the way, double click on shape, 3D shape. The way I did this thing in tutorial 7 was I created a reference point up there, because remember, analytical rigid surface needs a reference point. So I'm in that part. Let's go to essential. Let's create a point, and the point is 500 millimeter up, and it's there. You can see that right there. What I then did was to draw a line at 45 degrees and put the sphere at the end of it. So on this vertical plane, I sketched, okay, there is that point that I drew. I drew a line here. Okay, I want this point to be coincident with that point. This end control, I like using this instead of dimensioning. And then you go here, constraints using dialog box, and then say coincident. Oh, here, coincident. I could have put a dimension here and then the dimension, right click, either coincident, dimension 0. Now the length of this guy, is 500 millimeter, and this angle is 45 degrees. So this line and that line, let's try it again. Constraint between this line and that line on angle 1, 2, both of them selected. This line and this line, this axis, yep, 45 degrees. Okay, good. So exit. Now I'm going to create my sphere at the very end. Sphere is a surface, so you'll find it in surfaces, and it is the place that you find extrude and revolve and things like that. There's a sphere here. So the center is this point, and default axis is fine. Radius is 37.5. 37.5. What's the radius? Sorry, 37.5. 37.5. Okay, now if you look carefully, you see that this is not the full sphere yet, but with these numbers you can control the how it closes. So minus 90, go all the way around. Notice that it went to minus 90. 90, it goes the other way, goes this way, and then this thing 360 to cover the other side. Okay, it's a full sphere now. Now, in tutorial 7, because this was going to be mesh, I put a material on this thing, but the material values were dummies, entirely dummies, okay? So here I don't have to do that, so I just leave it the way it is, okay? So now we're going to go to structure model creation. Okay, it's an empty FEM. Click on it. Now, it is important that you get this dialog box. If you don't, what I suggest is double click on the assembly, okay? And once you double clicked on it, you end up in the assembly design, and then double click on this thing. It's important to get this thing, okay? Because it asks you what parts do you want to participate in this analysis. So I want both of these, okay? You say okay, good. Let's go ahead and mesh our plate first. So mesh, surface quad mesh. You select that. I believe 6 millimeter is what I wanted. And then you say mesh, and it's going to mesh that thing for you right there. Now, I don't want to mesh this because I'm going to do this in analytical rigid surface. But you will see that the limitation of analytical rigid surface is going to come and bite us. You'll see why. So first you click on the abstraction tab. Here's the abstraction tab. Oh, before I do that, let me also put the material, the section properties here before I forget. So properties, shell section, on that, and the proper material is picked, and the thickness is 2 millimeters, right? Okay, good. Now back to what I was talking about. You go to abstractions tab, and notice that here you can do rigid body, which I don't want to do. I want to do analytical rigid surface. You click on it, and you try to pick this. Nothing can be picked. Basically, the sphere, nothing can be picked. Even if you went to the sphere and you tried to pick the stuff from the tree, nothing will be picked. There is a reason. Analytical rigid surface must be a, a surface that is obtained by revolution about an axis or a line, or is extruded in a certain direction. This was a primitive that I made, which was a sphere. That does not count. That's why I cannot create this turn this to analytical rigid surface. So I have to bite the bullet, go to the sphere, delete this, go to this part, delete this primitive. Okay, so we go here, go back to this. Unfortunately, we have to do that. Go there, go there. Let me see if we can deactivate stuff. Maybe we deactivate it. May do, may be okay. But you know what? I'm going to delete it. I'm going to delete this. I'm going to delete this. Okay. So what I have to do is to have to draw a half a circle perhaps and revolve about 360 degrees. So here, because I have all the machinery needed, I'm going to do it like this. I go to the sketch, the one that I drew this line in, double click on it. Okay. First thing I'm going to do is I'm going to make this thing a construction curve. And how do you do that? You select it. There's a construction element. It turned to construction. Because when I draw half a circle here, and I try to revolve it without this being construction, it says that the sketch is self-intersecting. But when you turn this into a construction curve, it doesn't care. So let's go and do the arc. The different ways of doing it. One is arc. The center of the arc is here. It's going to go from there 180 degrees. I hope that this actually is 180 degrees. I'm not sure. Well, we can actually fix that. So let me see for a second. Let me do the following. Let me draw a line here. Make sure that it looks good. It looks good. I bet this is 180 degrees. If not, when we revolve it, we see that there's going to be a seam there, so or a gap there. Okay, no problem. Now let's give it a radius. The radius is 37.5. Okay, and then we exit, and that sketch. Oh, that the thing is that you know what? Because I turned that thing into construction, I cannot see it. So let's go back to that sketch one more time. Okay, I will turn this into an axis. Okay, so let's see, where is the axis? Must be somewhere here. Line. Instead of construction is fine, but I will turn this into an axis, or I'll make an axis here. How about that? Okay, good. And exit and revolve it. Because when you do an axis in that sketch, automatically it revolves it about that. But if it's a construction, then I have to pick it, and it's obviously won't let me do that. So 360. The moral of the story is that you have to draw something that looks like a sphere by taking a curve and revolving it about something. Okay, and we say okay, and there we are. Now when we go to the finite element and select the abstraction and select the analytical rigid surface, I should be able to pick this. There we are. And the reference point is that point. And we say, okay. Okay, so let's see now. The limitation of the analytical rigid surface was demonstrated. I could not use the primitive sphere directly to turn it into an analytical rigid surface. I had to bite the bullet, delete the sphere, and create it by revolving a semicircle about a line or an axis. Too bad. Okay, so this is an analytical rigid surface. You can see that, and there is a point here that we will actually use to put our information on. I think that's pretty much it. So let's go to our scenario. Remember, you have to do it in mechanical scenario creation application, because that has the explicit dynamics analysis software in it. You click on it. It is a structural, and the finite element mesh was created. Now, the one that I have here is, let me see for a second. What's the number here? 17069. Oh, 17068. Sorry, this is 8. This other one must have been, oh, it's sitting there from some other analysis. Never mind. It's this one that you want to do, okay? It's this model. Good. And we go to procedure, explicit dynamics analysis, duration 0.025 seconds. You say okay. Okay. So let's go and apply our boundary conditions. Clamp all the way around this. Now remember, if you cannot pick these edges, it's because that sketch is blocking your view. So let's go and hide that sketch, which is on their plate, right? The sketch. You hide it. Now I should be able to pick things. 1, 2, 3, and 4. You say okay. Let's fix this point. This is the reference point for that analytical rigid surface. So let's go ahead and actually apply the proper boundary conditions there. So fix displacement. This point, this vertex, does not translate in X, Y, Z. By the way, I could have selected the point from the tree directly. There was a point here. And it can rotate about Y. Good. Let's give it an initial, not initial, but let's give it a rotational velocity, applied rotational velocity right there. And the point is again that point right there. And 75 rad per second. That's what the speed was. And it's about the Z, y-axis right there. You can see that. All right. We go and define our friction coefficient under interaction. First of all, this is where we define our friction coefficient, 0.3. Okay. And we do general contact with the appropriate coefficient that we specified, contact property 1. I could have given it a name, but anyway, it's this one. We say okay. Let's change our element size, element type. So if you go to structural case analysis, structure analysis case, under the element type assignment, double click on this, and I make it reduced. Okay, I don't think I've forgotten anything. So let's go ahead and first of all save this. All right, we go to simulate. Let's do a model check, quick model check. Oh, hopefully this is the right ID. Yep. Okay, good. And then a simulation check. I'm glad that I did this problem two ways, one with analytical rigid surface that we're doing now, and the other one with uh, the rigid body, because there are certain things that popped up when we did analytical rigid surface that it would not have been trivial, but Anyway, I'm glad I did it. Close it, and then now we're going to run it. Oh, I forgot to put the put point inertia. Oh my God. I forgot to specify the mass here. We have to go and fix it. There is no mass here. Let's see. It's going to run, but it's going to be garbage because this sphere, this thing has no mass associated with it. So let me cancel this thing and go and apply my mass. So let's go to we have to go to the meshing basically right here. We have to go there, which means will have been the model under the abstraction point inertia right there, and this point, and 1.5 kilograms, 1.5 kilogram, which is 0.002 tons. Oops, let's see, 1.5 kilogram, which is going to turn into 0.002. Actually, it's 1.5, but carries 40 tons. Now, these things I specified in the tutorial 7 because I said that I'm doing exactly what the guy in the YouTube is doing on the ABAQUS CAE. Those are totally unnecessary. And I mentioned that totally unnecessary, so I'm not going to specify it here. So we say, okay, wow, you know that we're about to run this thing without actually having a mass there. Okay, so we go to scenario again. We can do this once again. So this is the model check. That's going to be quick, done. And this is going to be a simulation check. Okay. As I pointed out in tutorial 7, this sphere could have been placed very close to the plate and done the same problem. I put it at a 45-degree angle, which is totally was unnecessary, unwarranted. But for visual purposes, it may look better. Now we're running it. It hasn't started yet. Once that, okay, now it's going to start. And it's not going to take very long, I'm pretty sure. So check the iterations. It should go by very quickly, reach 0.0025. I want to emphasize again, not every problem can be done with analytical rigid surface. I just showed you the case that even a sphere, if you make it as a primitive, it's not going to be solvable with analytical. Analytical rigid surface must meet those limitations. Okay, this is done. Limitations are either it should have been created from an extrusion or from revolving about a particular axis. Okay, so let me close that. Yep, very good. So let's animate this. This is the von Mises stress. Good. So, that takes care of things.